Hi, I'm Dr. Incognito. In this video, we're going to discover where a function is concave up and where the graph of a function is concave down. And to do this, we're going to use the second derivative. The theory tells us that if f double prime is positive on an open interval, if f double prime is positive on an open interval I, then f is concave up on the interval, which means that it's got the same curvature as the letter U. And if f double prime is negative on an open interval I, then f is concave down on the interval I. So it has the same curvature as an upside down U. Okay, so let's look at a couple of examples. We will begin with a cubic polynomial, 2x cubed plus 3x squared minus 36x plus 2. Let's see where this cubic polynomial is concave up and concave down. So where is f concave up versus concave down? We calculate the second derivative of f. So f prime is 6x squared plus 6x minus 36. And f double prime is 12x plus 6. And we want to know where is 12x plus 6 positive and where is 12x plus 6 negative. So it might be easiest to set this equal to 0. If 12x plus 6 is equal to 0, then 12x is equal to negative 6. X is negative 6 over 12, which is negative 1/2. So when x is negative 1/2, the second derivative is equal to 0. To the left, it will be either positive or negative, and to the right, it will be either positive or negative. It won't be 0. So let's check on the interval negative infinity to negative 1/2 to see if f double prime is positive or negative. Let's just throw the number negative 1 in there. F double prime of negative 1. Here's f double prime here. If you put negative 1 in for x, you get negative 12 plus 6, which is negative 6. And the important thing is that it's negative, and that means that the function is concave down on this interval from negative infinity to negative 1/2. And then if we try 1, f double prime of 1, that's going to be 12 plus 6, which is 18, which is positive. And so f is concave up on the interval from negative 1/2 to infinity, concave up. One more thing could be said. When you have a transition from concave down to concave up, when you have a transition point on the graph, then that point is called a point of inflection, or an inflection point. So f has an inflection point at x equals negative 1/2. Okay, let's look at another example. Let's take a look at the function f of x equals e to the negative x squared. F of x equals e to the negative x squared. So where is f concave up? Where is it concave down? And find the inflection points while we're at it. Find the inflection points. So this function is continuous for all x. To figure out where it's concave up and where it's concave down, we need to examine the second derivative. Where is the second derivative positive and where is the second derivative negative? So first calculate f prime using the chain rule. It's e to the negative x squared times negative 2x. The derivative of the exponential is itself times the derivative of the inside, which is the exponent, negative x squared. The derivative is negative 2x. And then the second derivative is going to require the product rule. So the first, e to the negative x squared times the derivative of the second, which is negative 2. And then plus the second, which is negative 2x, times the derivative of the first, the derivative of e to the negative x squared. Well, that was our original function, so the derivative of that piece is exactly what we have here. E to the negative x squared times negative 2x. Now if we factor out the exponential e to the negative x squared, we're left with negative 2 plus negative 2x times negative 2x is positive 4x squared. And I think I'd prefer to write this as 4x squared minus 2 here times e to the negative x squared. So there is our second derivative, 4x squared minus 2 times e to the negative x squared. That's f double prime. Now we want to see where this is positive and where this is negative, so we should keep in mind that an exponential is always positive. So whether this second derivative is positive or negative will depend completely on this polynomial 4x squared minus 2. So I want to know where is that polynomial positive, where is that polynomial negative. So I think the easiest thing to do is to figure out where the polynomial is equal to 0, and then go from there like we did in the last example, testing the intervals. So 4x squared minus 2 equals 0. 4x squared is 2. X squared is 2 over 4, which is a half. X is plus or minus the square root of a half. So in other words, x is negative 1 over the square root of 2, or x is positive 1 over the square root of 2. And these numbers, 1 over the square root of 2 is approximately, let's just say 0.7. It's approximately 0.7. That will help us to choose a test point, knowing that it's approximately 0.7. So I draw a number line, and I put these two values, negative 1 over the square root of 2 and 1 over the square root of 2, on the number line. So I have three intervals from negative infinity to negative 1 over root 2, in between from negative 1 over root 2 to 1 over root 2, and then to the right, 1 over root 2 to infinity. I want to know on each of these intervals, is f double prime positive or negative? So I do a test point. That number is about negative 0.7, so I can put negative 1 in. What is f double prime of negative 1? F double prime is here in the box. I check the polynomial. If x is negative 1, I get 4 minus 2, which is 2. So that's positive. That means that f is concave up on this interval. F is concave up. And between negative 1 over root 2 and 1 over root 2, you'll find 0. So let's test f double prime of 0. If x is 0, then we have 0 minus 2, which is negative. Again, the exponential is positive, so I don't have to worry about that. The polynomial when x is 0 is negative, so f double prime is negative, which means f is concave down. And finally, for the last interval, the test point, since that number is approximately 0.7, the test point would be 1. F double prime of 1 is the same as f double prime of negative 1. It's going to be 4 minus 2 for that polynomial, which is positive, and so f is concave up. So it went concave up, concave down, concave up. So the answer to the question, the final answer is F is concave up on the intervals, there were two, on the intervals negative infinity to negative 1 over root 2 and 1 over root 2 to infinity. And F is concave down on the interval, there was only one, that was in the middle, the interval from negative 1 over root 2 to 1 over root 2. Where are the inflection points when you have a transition point on the graph in the concavity from either up to down or down to up, then you have an inflection point. So there are inflection points at both negative 1 over root 2 and 1 over root 2. At x equals negative 1 over root 2 and x equals positive 1 over root 2. These are inflection points, transitions in the concavity. The first one, transition from concave up to concave down, and the second, transition from concave down to concave up. If we look at the graph of this function, if you wanted to plug this function into your calculator and look at the graph, you would see that it looks something like this. This is an example of a bell curve, and here you see the curve is concave up. You get to a certain point right there, and then it transitions to concave down, and then on the other side, it transitions back to concave up. This is negative 1 over root 2. This is 1 over root 2. Those are our inflection points, because we have concave up, and then a transition at this point to concave down, and then a transition at this other point back to concave up. Okay, so that's how we can find where a function is concave up, where it's concave down, and find the inflection points. Thank you for watching.